I want to take you back to our original QFT, where we tried to ask ourselves what questions we would have to have answered in order to describe the motion of a ball. And we agonized about all these, what kind of ball is it? What is its shape? Is it aerodynamic? Is it fuzzy? Is it a golf ball? I don't know. Then we decided that we didn't really need to worry about that. If we were just describing its motion, what we needed to know was some initial conditions about the ball, whether it was confined to a track or the slope of a putting green or something like that. What kind of forces are involved? Is it being influenced by gravity or wind or anything else? And then we came down to, and I think this was the class, very insightful. I said, well, if we just had an equation of motion, we could describe it. And so here we are. We've gone through all of this. We're down to trying to find out some equations for how fast, how far, and how long. Please write down the 1, 2, 3, 4, 5 UAM variables. Delta x for displacement, delta t, change in time, Vf for final velocity, Vi initial velocity, and A for acceleration. Mr. Nick, tell me in your own words, what is acceleration? Change in velocity, that's not quite the whole story. Because you can, yes, Renee?
Change in velocity
over change in time. Because if you change velocity over a long period of time, that's a different acceleration than if you change that same velocity over a short period of time. If I use symbols to write that, then I would say A is equal to delta, a change in velocity, over delta, a change in time. And what we've seen in previous sections when we were talking about the speed equation, we further defined this change in as the difference between the final velocity and the initial velocity. So we can write change in velocity as the final velocity minus the initial velocity. And I'm going to leave delta t in the denominator just for a minute. If I wanted to, with this working definition of acceleration, now I can do a couple of other things. If I wanted to rewrite this in terms of the change in velocity, then I could rearrange this equation and I could say the final velocity minus the initial velocity is equal to acceleration times the change in time. Could I not? I've just rearranged this equation, multiplying both sides by delta t. And this brings us to our first uniform accelerated motion equation. Now what I'm going to do is I'm going to rewrite this and just solve for Vf so that I have the final velocity is equal to the initial velocity plus acceleration times the change in time. And this is what your book has. I'd put a big box around that because that's going to be our first UAM equation. You could rewrite that as the change in velocity is equal to the acceleration times the change in time. Okay, and the reason I did that was because sometimes in a word problem, it might say an object at rest, velocity is 0, and then it gets up to a speed of 20 meters per second. So the Vf would be 20. Another problem might just say the change in velocity is. We've got our first equation for how fast will the object be going if we know certain initial conditions. So this is why I'm doing this whole presentation, is to try to answer these questions: how fast, how far, and how long. Let me ask you, if you knew how fast something was going for a certain amount of time, what else would you know? If you knew something was, how did I write that? If we knew how long something was going at a certain speed, what else could you tell me? What? We know how much time it's taken, and we know how fast it's going. Sophia?
The distance?
We would know what distance it is, right? Right? So that's the old, remember the triangle, right? So speed is equal to distance divided by time. And if we knew this, what the speed was, and we knew what the time was, then we could find the distance, right? So that's a little gimmick I teach my freshmen, right? So now we're in physics, and now we use these fancier symbols. If we know the speed and the time, then we know the distance, right? All right? Okay, so mathematically, those are symbols for that. And we also studied the graphs. Let me see if I can make some connections for you graphically. If this was a velocity versus time graph, and an object was traveling at a constant speed, my question to you was if we knew how fast the object was going over a certain amount of time, would we be able to determine the displacement or the distance traveled? And Hussein is nodding his head. And so we said, well, yes, all we have to do is multiply the speed times the time, right? All we have to do is multiply the speed times the time. All we have to do is find the area of the rectangle. Isn't that what I just did? How do you calculate the area of a rectangle, Mr. Rios?
Side times the length.
Right, the side times the length. In this case, the side is the velocity that we're traveling, and then the length is the time, right? So another way to say this, I don't know if you've ever heard anybody say something like, just calculate the area under the curve. And that'll tell you whatever it is you're looking for. If you, this is not a curve, it's a straight line, but it's okay. A straight line could be a curve. Curve could be a straight, no. If you just calculate the area under this line, and then you can find the displacement, right? So graphically, that's what we're doing mathematically here, right? Okay, good. I got you guys nodding your head. But this is not accelerated motion, isn't it? This is constant speed. All right? Well, I think what we'll find out is this still holds true. If you, that's my graph's a little sick there. Sick in a bad way. Okay, so velocity versus time. I'm still wanting to figure out what my displacement is. But in accelerated motion, which is the topic of today's lecture, in hillbilly terms, that means it's speeding up, right? So in the terms of velocity versus time, it's speeding up. So if we apply the concept that we just learned about calculating the area under the curve, how would I calculate the area of this shape? Yep.
Half of base times height, so half of the time times the velocity.
Okay, 1/2 the base times the height, right? TV. Would it matter if I wrote it instead of TV, could I write it VT? It doesn't matter, right? Okay. And this holds true no matter whether it's a positive slope or a negative slope. It just has to be a constant slope. Okay? So delta x equals 1/2 VT. All right. This is where I get a little bit bogged down. And if you get confused, go to page 71 in your textbook, and they do a really good job of explaining this. I'm trying to get to our next uniform accelerated motion equation. Let me take this a step further. This is accelerated motion here. But what if we had some initial velocity? just take the graph that I put up there before, which was a rectangle. Some initial velocity, and then we speed up from there. So now we could write our displacement as delta x would be the, I'm going to put total here, would be the delta x that we got from the rectangle plus delta x that we get from the triangle. Okay, you don't need to write down all these notes. What I'm really wanting you to get to is here, but I just think it makes everybody feel better if we know where all these came from. It's just more satisfying. All right, so delta x rectangle was, all right, maybe I shouldn't erase that. Delta x rectangle was equal to the change in the velocity over time. And then the triangle was 1/2, not the change in velocity, VT. And then the triangle was 1/2 VT. Okay? Now here's where, so this would be the velocity associated with this, and this would be the velocity, the changing velocity associated with that. Here's where it gets a little bit weird. I'm going to plug in a delta t for this v right here and write this equation like this. Okay, this is where it gets a little bit hokey, and you're like, well, why did you do this? Because I want a position with average acceleration equation. So I'm going to write this now as delta x is equal to whatever our initial position was plus the initial velocity times time plus 1/2 a delta t squared. Made a mistake. I've got different, this is confusing. This is not a delta. This is our x final, this is our x initial. And that is what your book has. Okay. Okay. I want to write it slightly different below here. And this is not, let me make an I there because I'm using my symbols. Initial. And to be proper, this is average acceleration. I'm going to rewrite this slightly different by saying now this is a change in position because we have our f of x and our final position and our initial position. I can make that a change in displacement if I rewrite the equation this way. Okay. This has got 3 terms, solving for the final position. This has got 2 terms, solving for the change in position. And the reason I'm giving you both of these because some word problems will say, hey, I start at x equals 2. Where am I going to end up? Or the word problem might say, the change in position during the acceleration was 10 meters. You're going to get problems both ways, where you'll have to enter in a position, and you'll have to enter in position information, or you'll have to enter in a change. Okay? All right. Sorry if I'm stumbling here. It's difficult stuff, but page 71 in your book does a really good job. Also on page 71, they give an alternate equation. These are all related, So you can solve for different variables and rearrange the equation. The alternate equation given on page 71, final velocity squared is equal to the initial velocity squared plus 2a x final minus x initial. This one is in your book.
What does that last equation find?
This is finding final velocity. You'd have to unsquare it, but it's finding. So this is finding final velocity when you know the initial velocity and the acceleration and the time. This is finding the final velocity if you know the initial velocity and the acceleration and the change in position. So what they've done is they have substituted. They've made a substitution here to get this. Bottom of page 71 shows you how to do that. All right. If you are a flippin' physics fan, you had a question, Nick?
I understand everything, except why is this t squared on the second equation?
Because when I put this in here, then I had t times t. Okay. If you're a flippin' physics fan, he gives us one more. Change in position is equal to 1/2 the final velocity plus the initial velocity times the time. It turns out that it was funny because you're going to get some problems in a minute, and then the last problem is a challenge problem. But it turns out if you have this equation, it's not a challenge. Okay. Let me sum it up. These three are in your book. This fourth one is thank you, Mr. P. How many variables do we have? How many variables do we have? How many variables do we have? 5. How many equations do we have? 4. It turns out if you know any 3 of these variables, you can solve for the other 2 and make one happy physics student. All right? So let's try that again. How many variables do we have? 5. How many equations do we have? 4. If we know any 3, we can solve for the other and make one happy physics student. All right. Okay. Let's do problem.